Okay, for cable, different size already you know, AWG 3, 4, 1, 2, 4, 6 like this, and here one problem is here. Calculate voltage drop, okay, and energy wasted in AWG size for 4500 feet long cable, temperature 350 degree Fahrenheit, okay, resistance 77 degree Fahrenheit, and resistance of the conductor 77 degree Fahrenheit is given 0.271 ohms per 1000 feet. Motor current is given 30 ampere. The solution is simple. RT total resistance equals L length into resistance per 1000 feet. Okay, this into 1 plus 0.00214. This is constant for copper wire. Then T minus 77. This is the formula. Okay. So if I put the formula for voltage drop, so for first you calculate RT. RT means L into R divided by 1000. L is given, well, L value is given here. L is 4500 feet into R value is given 0.271 divided 1000, 1 plus 0.00214, T is given 350 minus 77. Okay, so whole calculation gives 2.5 ohm. So power loss P equals 3I square into RT, R capital T I have given, divide by 1000. Okay, so this value will come 3 into I means current is given here somewhere, resistance this one 30 square into RT 2.5 divided 1000. So this is giving 6.8 kilowatt. Okay. So this way you are calculating power and voltage. So another problem, find total resistance 6000 feet cable at an average cable temperature 300 degree Fahrenheit, specific resistance 77 degree Fahrenheit, and R value also given. So again simple formula, RT equals 6000 into 0.16 you are given, okay, 0.16 divided by 1000. This is simple formula, 1 plus 0.0214, 300 minus 77 equals 1.42. Okay, Ohm's symbol is like this, okay, like opposite of picture. So if you are using longer cable, so your RT or resistance will be higher, so voltage drop will be higher. Pothead MLE or motor lead extension. The term is used in motor lead extension. So I got a good picture from Baker Hughes' website. So just I copied from there. Okay. So there are several pictures available, but I found this is very nice picture. So this will be connected here, but it must be insulated properly. If you are not insulating properly, water will enter and that will be gone. So this is your motor actually. This is your cable. Okay, this is your cable, and this will be connected directly to this one. So special power cable from Pothead motor above the end the pump, and if you want to find a specification, then you have to go API RP11S4. So API RP11, I think this is for artificial lifting system. So ASR, so that way they divided, many documents are there. So you can go through those documents. A low profile cable flat configuration can be used for limited space available, but if you have larger space, then actually you can use circular cable. But nearby motor stage, so motor will take certain space, and after motor there will be some very limited space. In that case, you can use flat part, but other part may be circular cable. Length at least 6 feet longer than the upper end of the pump. So motor to motor, then protector, then pump, the upper end of the pump to the motor, certain length is there. So, it's plus 6 feet, that much of long flat cable you have to give. So, that one is actually your MLE, motor lead extension. So, that will be normally a flat part and it is connected to your Pothead. So, Pothead should have some pins also to secure, so that you can thread it properly, so that there will be no, if there is a small movement of the cable, it should not go out of the system. So, that way you are securing this MLE and Pothead. VFD we are using in my laboratory. Actually, this picture I have shown already. We have one VFD, variable frequency drive. What do we do? We change our speed using VFD, variable frequency drive, and if we change electrical frequency, my motor speed will change. Motor speed changing means my centrifugal pump performance will change. Normally the speed and performance HQ curve, if you remember, normally I have drawn like this. If I reduce the speed, then my HQ will be like this, N1, N2, N3. If I increase speed, then we going like this. Okay. So VFD also has their different names: adjustable frequency drive, adjustable speed drive, variable speed drive, AC drive, micro. So many names are there. Whenever you are reading document, so you should know the different names people call. If you do not name, what will happen in exam? If I give some name, say micro drive, so you say, sir, you did not teach it. All right. So you should know all the alternative names also. Whenever you are going for interview also, you should know the different names, so that interview board people, if they want to play a trick, they want to call by different name, and you say, sir, I don't know, although you may be knowing because of name difference. So that will not be good. So better you know all the names. Normally VFD will be used for your induction motor systems, power electronics based device, control frequency, okay, and voltage. And frequency and voltage is changed, you can change your motor speed. Okay. In ESP system, in 3 stage you do your induction motor speed change. It will be 3-phase motor normally, right? So rectifier stage, inverter stage, control system stage. So first you rectify 3-phase 50 hertz frequency from 220 to 440 volt. Okay. So you are changing voltage, and now you can change frequency also, output frequency. I wrote HZ, actually it should be written as frequency. Okay, output voltage. So you should know, because I made a short form, like OP means output, V means voltage. So this is output voltage. Output okay. Control system controls output voltage, maintains constant voltage, and hertz as motor. Hertz means frequency, voltage and frequency. Number of poles, this formula I have already shown you actually. So now I need to discuss again the same formula. So your motor system, motor electrical system will have bearings and thrust bearings. What is bearing? Bearing actually when one shaft is rotating, okay, and let us say shaft rotating inside this one, there is one impeller or motor coil, this is rotor rotating, and if it is rotating here and it is lots of friction, then lots of energy loss will be there because of friction. Okay, so you give a certain gap, when you are giving gap, it will be moving like this randomly. Okay, so you are not allowed to move like this, it will create vibration. So what you do, you create some bearing. What is the bearing? So one will be radial bearing. Radial bearing is like this. Okay, radial bearing like this. Your shaft is here. Okay, shaft cross section. I can see this one, and it is rotating inside it. Okay, inside a certain thing, and you give small balls here. Like cycle shop you go, they will be putting lots of balls in your cycle, so that your cycle will be smoothly rotating. So this is called ball bearing. Okay. So this is called radial bearing also. Okay. So radial bearing will have one shaft is here. Okay. Shaft will be rotating here, and in between this outer casing and this shaft, lots of balls will be there. Okay, if you go to a cycle shop, they will be putting lots of balls in your cycle. You see, if you are feeling very much difficult to running by your cycle, go to cycle shop, they will be removing the old balls and they will put new balls, and they will put lots of grease and oils also. Okay, so that way the friction will be reduced, it will be rotating smoothly, and this will be holding radial load. Means because of this load, your load or shaft load, any load radially perpendicular to axis it is holding, then it is called radial load. In ESP system, radial load will be lower. Why? It is kept vertically rotating, so it is not giving any extra force towards perpendicular to the axis, right? Perpendicular to the axis, there is no load, almost no load. There will be some load because of this misalignment and other issues, but we are assuming almost no load. But there must be radial bearing, so that if any small load also there should not get any extra friction or resistance or bend, and it should get smooth rotation. Okay, and when it is rotating, you need some lubricating oil. Okay, so if it is motor is having already your dielectric fluid, so that will be lubricating this bearing area. If it is not lubricating, lubrication means you are reducing friction. Bearing purpose also reduce friction, but still there is some friction. You give some lubricating oil, so you reduce further friction. This is called anti-friction bearing actually. So your friction will be almost negligible. Okay, because you created ball bearing plus this one, and there are different types of bearings also available, for example, roller bearing, ball bearing, journal bearing. Okay, so we are not discussing details of this one, but bearing works like this. Normally ball bearing will be used in many places, especially in bicycle. Simple. Okay, ESP system also you can use journal bearing, ball bearing, or roller bearing. Next is thrust bearing. What is thrust bearing? Thrust bearing means, like, I have motor here. Okay, motor is having one stator, outside stator, one rotor. Okay, when you're rotating, I said almost no radial load, but because this motor is having lots of magnet and coil and heavy metal, right? So because of metal, it is pulling down. When it's pulling down, that means you must hold it properly, otherwise it will go down, right? So then how to hold it? So you have to put thrust bearing. This axial load, actually it is getting loaded, so you call thrust bearing or thrust load. Okay, this is called thrust load. Okay, when it is by its own weight or its fluid weight or some other weight is there, and load is applying axially perpendicular to this axis, parallel to the axis on the top, then is getting axial load. And if you are not holding properly, then whole rod or whole shaft will be moving down. So it is not allowed to move down. So you have to go give thrust bearing. Here picture is there, thrust bearing. Okay. So here one cutout view I have taken. Again MLE is here, MLE. Okay, MLE is here. Your pothead is here. Okay, and thrust bearing is here. And these are the thrust bearing. What thrust bearing? This thrust bearing is like this. I have one bearing on flat surface here. Okay, and I have another flat surface, and I fix upper flat surface like this. Okay, I fix upper flat surface like this, and I have lower flat surface. You give extra load, so extra load will be coming here. It will go to this flat surface, and I have lower flat surface. And when it is rotating, both will be rotating together because I joined together. Now this flat surface joined with this one, it is rotating same speed, and when it is there, it will be rotating like this. Okay. So, but there is lots of friction. Can I put lots of balls? Okay, and give lubricating oil. So when it is forcing down and rotating, it will have almost no force, no friction. Sorry, almost no friction between two surfaces. Okay, so this surface will be holding this vertical load, whatever is there, and this will be fixed on your casing and outer casing, right? So the whole load will be going to this one. So this is giving load, but this is not taking any torque. This is taking only axial load. Okay, so this will take axial load, and this will be transferring to your outer casing, and shaft will be rotating, and all the axial force will be transferred to this one. Okay, here how this thrust bearing working here, you see this. Okay, okay, so one top plate is there. Okay, this is connected to shaft. Okay, shaft will have like this, and bottom plate will be having. okay, and shaft is, so shaft will be connected another plate in between, okay. It is like this, one top plate connected to your casing, shaft will have another plate and bottom will be another plate will be there. So, when shaft is rotating in between plate, the runner plate, they say runner plate will be rotating in between two bottom plate, another top plate. So, shaft will be connected to one runner plate. So, shaft will have one runner plate here, okay, and I have casing, okay. My shaft is here. I'll draw properly. My shaft is here, shaft will have one runner plate, okay, okay. This is my shaft and this is my casing or some outer casing, okay. So, casing is not rotating or not moving. So, casing will have some protruded part or that flat plate I said, okay, and the shaft will have fixed some flat plate. So, when shaft is rotating, this flat plate also will be rotating, this plate, okay, runner. And when it is rotating very high speed, it will be transferring all the axial force to this one, okay, axial force transferred, axial transferred, okay, but no radial. So, axial thrust bearing will take only axial load, not radial force, but radial bearing will take radial force, not axial force, okay. Some small amount of axial force or radial force can be taken, but majority, but maybe 90% load will be axial if it is a thrust bearing, fine, and it must be lubricated properly. If you are not lubricating, then there will be problem. And this shows the different laminations actually in motor, okay. Laminations means very thin sheets will be there, okay. Those is called laminations, and shaft will be passing this, okay. This is motor part, and this is called outer race, inner race, okay. Inner race will be connected to the shaft, outer race is fixed. So, shaft is rotating, outer race is not rotating, radial bearing. Thrust bearing, two plates are there in between the runner and shaft rotating, the axial force transferred to this bottom plate or top plate, and bottom plate, top plate connected to your fixed casing, shaft rotating, runner rotating together, okay. So, this way, and this radial and thrust bearing will be there in your pump also, in your motor also, in your protector section also. So, that extra force you are not transferring to other shaft. So, motor is producing certain amount of torque or uneven force also. So, uneven force should not go to your protector section. Protector section, if there is any uneven force, it should not transfer to pump, or opposite way also, pump should not transfer to protector, protector should not transfer to motor, okay. That is why this isolations or restrictions will be there in terms of bearing instead of coupling. Protector. So, I said like motor will have, motor is here, motor shaft is going to pump, okay, pump, motor. So, in between I will have one intake section, then I will have one protector section, CT or protector section, okay. What is protector section? Protector, like shaft is rotating continuously, right, and motor is here, motor is bottom, shaft is here, shaft is rotating continuously. So, this shaft entering somewhere to motor, so that means there will be some sealing arrangement and bearing arrangement, okay. And if sealing and bearing fails, then whole motor will fail. Let us say bearing working, sealing failed. What will happen? The internal motor fluid will be going out, liquid outside can enter, right? And subsurface temperature also changing because of motor running. Let's say initially motor inserted during installation stage, temperature low, okay, and when you give electricity, temperature high, temperature will be going up. Temperature going up means there will be some expansion of whole system, right? And liquid also will be expanding, and because of this high temperature, some liquid will try to go out of the system, and after long working life, the seal, motor seal will be there somewhere, right? Seal will be there somewhere. The seal will get damaged. Seal damaged means whole liquid will go out. Again, certain time your pump not working, temperature lower, outside fluid enter. High temperature fluid will try to go out, lower temperature. So because of temperature, fluid will get exchanged, and wear and tear also possible. So then once fluid exchange, your system will burn. So maximum motor failure occurs because of seal failure actually in submersible system. So what this submersible pump engineers thought, let's put separate one seal section. This will also be several feet long. This seal section will contain some bellows, some extra fluid chamber, some isolation chamber, so that if motor is having certain pressure loss because of the leakage or something, this protector section will supply extra fluid. It will give that much of protection, bearing, axial thrust, bearing, radial bearing, all these things will be there in protector section separately. So the motor will be running peacefully, because motor will say, I am producing torque, I don't want extra load, extra headache, I am busy with that. Then protector will say, okay, I'll protect you, I am the security for you, okay. Then protector will protect, then motor will be delivering torque to your pump, fine. So motor seal or protector section, different name again there, motor seal, equalizer, balance chamber, protector, different names are there, okay. Between intake and electric motor, intake means here, or gas separator will be there, okay. In between motor seal section will be there. So equalization, expansion, isolation, absorption, these four work it will do, okay. Equalization means pressure equalization it will be doing. Expansion, if fluid or something gets expanded, it will be capturing. Isolate, it will be isolating wellbore fluid and your motor fluid. Absorption, it will be absorbing then extra pressure or extra load. Equalizer will be pressure, it will be equalizing pressure in the wellbore with the pressure outside the motor. It will provide area for motor oil expansion. It will be isolating wellbore fluid of the motor. It will be absorb shaft thrust also, okay. And to do that, it will have some mechanical seal will be there, mechanical seal will be here, okay. Mechanical seal like face seal and radial seal, that sort of seals will be there, so that fluid can be isolated, wellbore fluid and your motor fluid, okay. And bag will be there, so expansion bag, some bags will be there, okay. So those bags will be contacting, expanding, and it will be giving enough space and a breathing space, you can say, okay. Provides expansion of volume and isolate clean motor oil. Elastomeric bag expands and contracts and creates barrier. Bag type installation at any well deviation can be used. Bag material durability depends on temperature and environment. Again, temperature high, so life will be lower, okay. So labyrinth chamber also will be there, so that you are creating it in multiple isolation or multiple separation, so that wellbore fluid should not enter. Radial bearing will be there, so that shaft vibration will be restricted, and axial thrust load also will be restricted. You will have thrust bearing. If you see this right side picture, there will be radial bearing here, okay, radial bearing. Then O-rings are there, O-ring bearing will be there, so that any outside leakage will be prevented. Then thrust bearing will be here somewhere, thrust runner, thrust bearing is here. So this thrust runner, you see the shaft is here, okay, shaft is connected to thrust runner. This is completely long shaft actually, okay. This shaft, motor is here and pump is here, okay. Pump intake or gas separator will be here, okay. Then it will go to pump, and it will be having thrust runner, thrust blocks are here. Okay, so this is outer casing. Okay, so outer casing fixing this thrust block, and your thrust runner is here. Okay, it is connected to your shaft rotating, thrust runner rotating, and thrust block helping or taking the thrust load or axial load in it and transferring to your casing. Casing will be fixed with other units. If you are not putting this thrust bearing or radial bearing, there will be multiple issues. So, because you do not want to transfer pump load to your motor want to work peacefully, okay, safely. Seals. Okay, so seals prevent leakage, containing pressure, excluding contamination. So, seal will be used for your motor. Motor is having its own seal. Again, you are giving extra seal in your protector. Okay, stationary seals also used for as a packing, stuffing box. Also, you are using like sucker pump. You can remember the stuffing box term we use. There also seal was there, and packing also will be used in wellbore. That term also used many times, and people will be using wellbore engineers will be using packers. Okay, so seals to prevent leakage. If there is only different fluid pressure, so seal if in between there, then and rotating part is there. So the rotating part, it will be rotating, but it will allow one fluid enter to another zone, or one fluid coming to another zone. So that way seal will be protecting the whole system. Okay, other than your ESP system, many other places also seals are used. Problem is like this: motor heat generation. How much heat is getting generated if motor is running? Motor heat generation means electric going, you are getting energy, but in between conversion happening. If you remember the thermodynamic laws, second law says like energy can be converted from one form, electrical to mechanical, one form to another form, but there will be some certain energy loss. That energy you cannot recover. That energy will be converted into heat. Okay, so when you are running your submersible system, submersible motor, there will be some energy loss. That means energy heat generation will be there. So how much heat is getting generated? If you do not calculate, then there will be problem. Okay, let's try to calculate it. Here one problem I have taken from ESP book. Calculate steady state skin temperature of an ESP motor with the following condition: casing drip diameter or casing inner diameter is given 5.5 inch, pump head 9000 feet, motor outer diameter 4.5 inch. Okay, casing 5.5 inch, motor 4.5 inch. So you have 1 inch only gap. Motor efficiency 75% assumed, motor length 15 feet, pump efficiency 0.6, water cut 75%, bottom hole temperature 200 degree Fahrenheit, oil heat capacity 0.5, water heat capacity 1. Okay, so this data is given. So based on that, you have to calculate steady state skin temperature of an ESP. So first, oil heat capacity C oil, water heat capacity CW is given. Okay, pump head H is given, motor motor length L is given, pump efficiency eta pump is given. Okay, water cut 75%. So C combined heat capacity, you will be CO into how much percentage there? Oil percentage 25.25, and water percentage C water into 0.7. Average heat capacity, it will be 0.875 BTU LB per degree Fahrenheit. Okay, so TF surface temperature, so H 1 minus okay, temperature is bulk temperature and the motor formula is 1 minus motor efficiency 0 eta motor divided by 778 C eta M eta P. So this formula gives 9000, 1 minus 0.75 motor efficiency given eta M divided by 778 into 0.875 into eta pump efficiency given 0.6. So this gives 7.4 degree Fahrenheit. Okay, because of this motor efficiency, you are getting 7.4 degree temperature increase. Now motor skin temperature. So here two assumptions you have to take. Otherwise in book it is given like you have to use table or some other thing. So let's assume here in problem I will give them. Motor skin temperature increase, del T equals 30 degree Fahrenheit, and convective heat transfer coefficient you take 0.035 BTU SFT square degree Fahrenheit. Okay, so average T temperature, average temperature is, so TF del TF equals H equals 200 plus 7.4, 207.4 degree Fahrenheit. That's 200. Del TF equals 200 plus 7.4, 207. So 200 is given here, bottom hole temperature is given here actually. So you are getting this one. So next is T average temperature you calculate. T average equals TF divided by del TF by 2. So finally you are getting 207.4 plus 15 equals 222.4 degree Fahrenheit. So H is given 0.035. If it is not given, then there is long process to calculate. Better not to go through long process, rather you make it simpler. So BTU per second FT square degree Fahrenheit. So motor skin temperature, TS equals 2.7 into 60, 15 into 4.5 into 0.035 divided by 1 by eta m minus 1. So this will give 22.6 degree Fahrenheit. So this is formula is like this: 2.7 bhp divided by L motor D motor one okay. So this 22.6 degree Fahrenheit temperature rise will be there. Okay, thank you very much for today's lecture.